Welcome back to Honors Calculus. In this video, we're going to continue our discussion of the derivative, looking at how to evaluate a differential or the differential function of a function, which is going to seem like something completely different at first, and then wrap around and give us something exactly what we were talking about in the last video. So consider a function f from the real numbers to the real number, the real valued function. And then let's let c be a real number constant. The difference quotient of f at c is given by f of x minus f of c all over x minus c. Right. The differential of f is a new function, which we call f prime. All right, so it's f with an apostrophe after it, which is read as f prime. And we define f prime at a point c as f prime of c is the limit as x approaches c of the difference quotient, f of x minus f of c all over x minus c. So for example, if I have the function f of x given by x over x plus 1, I might try to evaluate the differential function f prime at 2. By definition, f prime of 2 is f of x, x over x plus 1 minus f of c, c over c plus 1, all over x minus c. And I left out a very important part of this. Let's try that again. I don't just want this fraction. I need to take the limit as x approaches c of this fraction. And if we plug in that c is 2, I guess we can make this a little bit more pleasant to look at. There are a couple of ways to deal with compound fractions. The first thing I want to point out is if you plug in x equals 2, you are going to get 0 over 0. It's a long way to go to get there, but that's 2 over 2 plus 1 minus 2 over 2 plus 1 all over 2 minus 2. And we have fraction minus itself, which is 0 over 2 minus 2, which is clearly 0. So instead, we're going to look for ways of reducing this fraction and hope that we can get out of the problem, hope we can remove this indeterminate point. There are a couple of ways to approach a fraction that has fractions in it. My personal favorite approach is to try to find a common denominator in the numerator, common denominator in the denominator, and then rewrite the whole thing as a giant division problem. So let's take x over x plus 1. Let's notice that 2 over 2 plus 1 is the same thing as 2/3. And in those fractions in the numerator, we can find a common denominator by multiplying the first fraction top and bottom by 3. And multiplying the second fraction top and bottom by x plus 1. All right, so now we have the limit as x goes to 2 of 3x minus 2x minus 2 all over 3 times x plus 1 all over x minus 2. And hey, once again, we can simplify here. This is the limit as x goes to 2 of 3x minus 2x is x minus 2 over 3 times x plus 1, right? That's the fraction in the numerator. And then that whole thing is over x minus 2. At this point, you probably see where we're going, but I'll take my time and be careful with this. All right, since it went off the top of the page, remember the thing we're looking for is f prime of 2, which is the limit as x approaches 2 of this whole thing. You can rewrite a compound fraction as division. This is x minus 2 over 3 times x plus 1 divided by x minus 2. Which is the same thing as multiplying by 1 over x minus 2. And finally, we get to the point where there's an x minus 2 in the numerator and an x minus 2 in the denominator that cancel each other out, leaving me with 1 over 3 times x plus 1. And this I can evaluate when x is equal to 2. 1 over 3 times 2 plus 1, which is 1 over 9. Right. I didn't say it was easy. I just said it wasn't that hard. Right. Nothing challenging about this, nothing exotic or esoteric, just a whole bunch of careful algebra manipulations. All right. So now that we have a decent idea of this idea of a differential, and that takes us to this theorem. For the graph y equals f of x, the differential f prime at c is equivalent to the slope of the tangent line dy dx at the point x equals c. We are going to, later on in this course, get into a couple of places where the subtlety of the difference between these two ideas becomes important. the one that I want to point out to you that is kind of obvious once you stop thinking strictly in terms of functions, but that's the left-hand side is only defined for a function. The right-hand side, the slope of a tangent line, is defined for any curve. We've only calculated what it looks like for a curve given as y equals f of x, but we will, a little bit later in this course, take a look at some curves that are not functions, and we will still be able to calculate the equation of a tangent line by using a very similar structure to find the slope of a tangent line. So that's a place where slope is more valuable. This idea of differential is more valuable because it doesn't rely on the graph. There are some functions out there whose graphs are very complicated. And trying to think about those functions in terms of a graph can be challenging and can be misleading. So being able to talk about a differential of a function without thinking about the graph y equals f of x has value as well. Each of these things is useful in different applications, so we have both of them. But we claim that they are equivalent, and the proof here is fairly straightforward. We start with f prime of c is the limit as x goes to c of f of x minus f of c all over x minus c. And we simply evaluate f prime at the point c equals x plus delta x. Well, that's going to be the limit as x approaches x plus delta x of f of x minus f of x plus delta x all over x minus x plus delta x. And now all we have to do is take a look at two small changes and everything will work out. The more obvious change is in the fraction. When I have subtraction in the numerator and also subtraction in the denominator of a fraction, if I switch both of those subtractions, the SIGN sign in top and bottom will change and cancel each other out, and we'll be left with an equivalent fraction. So I can easily write this as the limit as x approaches x plus delta x of f of x plus delta x minus f of x all over x plus delta x minus x. And now in that denominator, the x and minus x will cancel each other out. So we have the limit as x approaches x plus delta x of f of x plus delta x minus f of x all over delta x. Now the other issue is in that limit itself. As x goes to x plus delta x, right? Here I'm going to think about limits kind of in a daisy chain, limitception. Right? We know that the limit as delta x goes to 0 of x plus delta x is equal to x. And so if when delta x goes to 0, x plus delta x goes to x, we can flip that whole thing around and say that as x goes to x plus delta x, delta x must be going to 0. So that's how this thing can turn into the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. We could look into the details of the epsilon delta definition of a limit to prove that a little bit more carefully, but I don't think that it's worth the time to do so. So I'm going to leave things just like this. All right. So I would like you to take a look at the function f of x equals 12x minus 3x squared and evaluate f prime of 1. Notice here that this is the same problem that I asked you to look at in the previous video. In the previous video, I gave you the equation y equals 12x minus 3x squared, and I asked you to find the tangent line at x equals 1. In this video, I want you to look at this differential function, evaluate it, and demonstrate, looking at this particular example, that the two ideas of tangent line and differential are in fact equal to each other. So take a few minutes to write that out. Not just find f prime of 1, but verify, going back to your work in the previous video, that you get the same answer that you got for the slope on the last one using both of the methods. See what you can do with that one, and I'll see you in the next video.